welcome to this problem walkthrough. Today, we will be exploring LeetCode problem number 2000, reverse prefix of word. This problem challenges us to manipulate a string and reverse a segment based on specific criteria. Let's dive in and break it down step by step. In this problem, we are working with a string word and a character ch. The goal is to find the first occurrence of the character ch in the string and reverse the portion of the string from the beginning up to and including the index where ch is found. If ch does not appear in the string at all, the output should simply return the original string without any modifications. The input consists of a string word, which is made up of lowercase English letters and has a length between 1 and 250, along with a single lowercase letter ch. The output is the modified string after reversing the appropriate prefix or the unchanged string if ch is absent. Let's look at the first example. Here, the input string is ABCDFD and the character is D. The first occurrence of D is at index 3. To solve this, we reverse the substring from the start of the string up to index 3, which gives us tba. Then, we concatenate this reversed portion with the rest of the string, which remains unchanged as eft. The final result is dbeft. Now, consider the second example. The input string is 6 and the character is z. The first occurrence of z is at index 3. Reversing the substring from the beginning of the string to index 3 results in zxyx. When we append the rest of the string, xe, to this reversed segment, we get the output zxx. This demonstrates how the function handles a case where the target character is not at the start or end of the string. In the third example, the input string is ABCD and the character is z. Here, the character z does not appear in the string at all. Since there is no occurrence of ch, the string remains unchanged. The output is simply ABCD. This example highlights the condition where the function should return the input as is when the specified character is absent. Finally, let's discuss some edge cases. If the string contains only one character, such as word equals a and ch equals a, reversing the prefix has no effect, so the output is a. If the character ch is not in the string, the output is identical to the input, as seen in cases like word equals abc with ch equals x. When ch is the first character of the string, for example, word equals abc and ch equals a, the prefix reversal does not alter the string, so the output is abc. On the other hand, if ch is the last character, such as word equals abcde and ch equals e, the entire string is reversed, resulting in etba. These edge cases help clarify how the function should behave under different conditions. To tackle the problem of reversing the prefix of a word up to the first occurrence of a given character, we explored multiple strategies. The first and most straightforward approach is the brute force method. The intuition here is simple. We iterate through the string to locate the first occurrence of the character ch. Once we find its index, we extract the substring from the start of the string up to that index, reverse it, and then concatenate it with the remaining portion of the string. This approach is easy to conceptualize and implement. Specifically, the steps involve traversing the string, locating the character, reversing the required segment, and then combining the modified prefix with the rest of the string. If the character ch isn't found in the string, we simply return the original string as is. While this method is straightforward, it's important to consider its efficiency for larger inputs, which is something we'll address next. When analyzing the brute force method, we find that its time complexity is O(n), where n is the length of the string. This is because we perform a linear traversal to find the character, and reversing the substring is also a linear operation. On the other hand, the space complexity is O(n) as well, since creating a new reversed substring involves additional memory allocation. To improve upon this, we considered an optimized approach that performs the reversal in place. The intuition behind this optimized solution is to minimize memory usage by avoiding the creation of new substrings. Instead, we work directly with the string's mutable representation, such as a list of characters. We locate the first occurrence of ch, reverse the segment of the list up to that index directly, and then convert the modified list back into a string. This approach retains the linear time complexity for traversal and reversal but offers improved space efficiency, as the operations are performed directly on the list without additional copies. If the character ch isn't found, the original string is returned unchanged. The in-place reversal approach was ultimately chosen because it strikes the right balance between efficiency and memory usage. While the brute force method is easier to implement and may be suitable for simpler scenarios, it introduces unnecessary overhead from the creation of new substrings, which can be costly for larger strings. The in-place method, on the other hand, avoids this by operating directly on the mutable list representation of the string. A key insight here is that reversing a substring of length k is inherently an O(k) operation, which ensures that the algorithm scales well even for longer strings. By leveraging in-place modifications, we reduce memory overhead, making this approach more suitable for performance-critical applications. However, it is worth noting that the brute force method might be preferable in cases where code simplicity and readability are prioritized over optimization. All in all, the in-place reversal approach delivers a practical and efficient solution, especially for scenarios requiring optimized memory usage and performance. The problem reverse prefix of word requires us to manipulate a string based on the position of a specific character. The task is to reverse the portion of the string starting from the beginning and ending at the first occurrence of the given character. If the character doesn't exist in the string, the original string remains unchanged. To solve this, we follow a structured approach. First, we validate the inputs, ensuring the string isn't empty. If it is, we simply return the original string because there's nothing to process. Next, we locate the first occurrence of the specified character using the find method. This gives us the index of the character if it exists, otherwise, it returns -1. If the character isn't found, we skip the reversal step and just return the string as it is. After determining the position of the character, we divide the string into two parts. The first part, called the prefix, includes the substring from the start of the string up to and including the character we found. The second part, the suffix, is everything that comes after this prefix. Once we've identified these parts, the next step is to reverse the prefix. In Python, this can be done efficiently using slicing with the ::(-1) syntax. Finally, we combine the reversed prefix with the unchanged suffix to form the resulting string, which we then return. This step-by-step breakdown highlights the efficiency of the solution. The find method scans the string only once, and string slicing and reversal are optimized operations in Python. The algorithm ensures that the entire process is completed in linear time relative to the size of the input string. Now, looking at the data structures and complexity, this algorithm is simple and lightweight. The only data structure involved is the input string itself. Since Python strings are immutable, slicing and reversing operations create new strings, but no additional data structures like arrays or hash maps are used. This makes the algorithm in place in terms of how it handles memory. In terms of complexity, the time complexity is O(n), where n is the length of the string. This accounts for the find operation, as well as slicing and reversing, which process parts of the string. The space complexity is O(1), because no extra memory is allocated proportional to the input size, aside from the temporary strings created during slicing and concatenation. This balance of time and space efficiency ensures the algorithm is both fast and resource-friendly. To understand the algorithm better, let's walk through an example. Suppose the input is word equals ABCDF and CH equals D. First, we find the position of CH using word.find D, which gives us the index 3. Next, we slice the string into two parts. The prefix includes characters up to index 3, so prefix equals ABCD. The suffix starts from index 4 and includes the rest of the string, so suffix equals EF. We then reverse the prefix, which gives us reversed underscore prefix equals TBA. Finally, we concatenate the reversed prefix with the suffix to form the result, FIF. This is our final output, which is returned by the function. This example demonstrates how each step of the algorithm contributes to transforming the input into the desired output. Let's consider a few edge cases to ensure the algorithm works correctly in all scenarios. First, if the character CH is not found in the string, such as with word equals ABCDF and CH equals X, the find method returns -1. In this case, we simply return the original string unchanged. Another edge case is an empty string as input. For example, if word equals and CH equals A, there's nothing to process, so the empty string is returned as is. When the character ch is at the start of the string, as in word equals abcdf and ch equals a, the prefix is just the first character, which remains the same when reversed. Lastly, if the character is at the end of the string, such as word equals abcdf and ch equals f, the prefix includes the entire string. Reversing the prefix gives the entire string reversed, with an empty suffix. These scenarios highlight the robustness of the algorithm across different inputs. The solution to the problem reverse prefix of word is implemented in the reverse prefix method within the solution class. This function takes two inputs, a string word and a character ch. The goal is to reverse the portion of word from the start up to and including the first occurrence of ch, while leaving the remainder of the string unchanged. Let's break down the code step by step. 1. Finding the index of ch. The find method is used to locate the index of the first occurrence of ch in the string word. If ch is not found, find will return -1. This ensures that we can handle cases where ch does not exist in word. 2. Handling the edge case. If the index idx is -1, indicating ch is not in word, the function directly returns the original string word. This ensures the function behaves correctly for such scenarios. 3. Reversing the prefix. If ch is found, the function constructs the result string by taking the substring of word from the start up to idx plus 1, inclusive of ch, reversing it using slicing with ::-1. Concatenating the reversed prefix with the remainder of the string starting from idx plus 1. This implementation is efficient, with a time complexity of O(n), where n is the length of the string word. The find method and slicing operations both operate in linear time. The solution also handles edge cases like when word is empty or consists of a single character. The code is compact, easy to understand, and adheres to best practices for readability and performance. This is the Java implementation of LeetCode problem number 2000, reverse prefix of word. The logic mirrors the Python solution, using Java's index of method to locate the first occurrence of the character ch and string builder to reverse the prefix. The solution handles edge cases, such as when ch is not found, by directly returning the original word. In this example, we are given the word abcdfg and the character d. The first step is to find the index of the character d within the word. To do this, we use the find method, which returns the zero-based index of the first occurrence of the character. Here, d is found at index 3. Once we have the index, the next step is to reverse the prefix of the word up to and including this index. The prefix is the substring from the start of the word to index 3, which is abcd. Reversing this substring gives us tba. This forms the reversed prefix that we'll use in the next step. After reversing the prefix, the next step is to append the remaining part of the word. The portion of the word after index 3 is fk. To get the final result, we concatenate the reversed prefix, tba, with the remainder of the word, fk, resulting in tbefk. This is the transformed version of the word where the prefix up to the first occurrence of the character d has been reversed. The final output for this example is tbefk. In this example, we are working with the word hello and the character z. Here, the task starts the same way. We use the find method to locate the first occurrence of z. However, since z is not present in the word, find returns -1. This indicates that the character is not found. When the index is -1, we do not modify the word. Instead, we simply return the original word as it is. Therefore, the final output in this case is hello, since no reversal is performed. Now, let's consider the word racecar and the character r. The first step is to find the index of the first occurrence of r, which is at index 0. With this index, we extract the prefix of the word from the start up to and including index 0. In this case, the prefix is just r. Since the prefix only contains one character, reversing it does not change it, it remains r. This forms the reversed prefix, and we can now proceed to the final step. To complete the transformation, we append the rest of the word to the reversed prefix. The portion of the word after index 0 is acecar. By concatenating the reversed prefix, r, with the remainder of the word, acecar, we get the final result, racecar. In this specific case, the output matches the original word because the character to reverse around was the very first character. The final output is racecar. To analyze the time complexity of our solution, let's break it down into individual steps. The first step involves finding the index of the character ch using the find function. This function scans through the string, character by character, until it either finds the target character or reaches the end of the string. In the worst case, this requires examining every character, making it an O(n) operation, where n is the length of the string. Next, we create the reversed prefix by slicing the string up to the found index and reversing it. Slicing the string takes k time, where k is the length of the prefix, and reversing it also takes k time. Combining these operations, the total time complexity for this step becomes k plus k, which simplifies to ok. The next step is to append the remaining portion of the string to the reversed prefix. Slicing to create the remaining substring takes and ka time, where n is the total length of the string and k is the length of the prefix. However, when we concatenate the reversed prefix in this remaining part, the operation involves processing the entire string, so the concatenation itself takes n time. Putting all these steps together, the dominant operation in terms of time complexity is the n work required for finding the character and handling the string manipulations. As a result, the overall time complexity of the solution is n. Now, looking at space complexity, the input string is passed as an argument, and no additional space is explicitly allocated for it. When considering intermediate substrings, slicing operations like word idx plus 1 and word idx plus 1 create temporary substrings that require n space in total, as their combined length equals the length of the original string. Additionally, reversing the prefix creates another temporary substring, which takes k space, where k is the length of the prefix. However, since the prefix and the remaining substring together span the entire string, the total space required for these temporary substrings is still n. Finally, the output itself is a new string that combines the reversed prefix and the remaining part, requiring n space. Therefore, the space complexity of the solution is n, primarily due to the temporary substrings and the result string. When comparing this solution to a brute force approach, we find that both approaches are equally efficient in terms of time and space complexity. A naive method would involve manually iterating through the string to locate the character, reversing the prefix character by character, and appending the remaining part. This manual reversal of the prefix would add k time, but the total time complexity remains n, because the dominant factor is still the full traversal of the string. Similarly, the space complexity of the naive method would also be n, due to the storage of the output string. The optimized solution, however, leverages Python's highly efficient built-in slicing and string manipulation functions, making it cleaner and faster in practice, while maintaining the same complexity bounds. Analyzing the best, average, and worst cases, we observe that the time complexity remains n across all scenarios. In the best case, if the target character ch is found at the very beginning of the string, only the first character is reversed, and the remaining string is directly appended. This still involves slicing and concatenation, which take n time. In the average case, ch is typically found near the middle of the string, requiring n time for finding, slicing, and concatenation. In the worst case, if ch is not found at all, the find function scans the entire string, and the result is simply the original string. This operation also takes n time. Since the time complexity is n in all cases and the space complexity is n due to temporary substrings and the result string, this solution is both time and space efficient. When tackling this problem, there are a few common mistakes to watch out for. First, some solutions fail to handle cases where the character ch is not in the string at all. Assuming that ch is always present can lead to runtime errors or incorrect outputs. The safest approach is to include a guard condition, like checking if ch is not in the string, and simply returning the original input in such cases. Next, an incorrect index calculation for ch can cause issues, especially in programming languages where indexing starts at 0. Using methods like word.index ch in Python, for instance, ensures that you retrieve the correct position of the first occurrence of ch. Another common error is reversing the entire string instead of just the prefix up to ch. To avoid this, carefully extract and reverse only the substring up to and including the index of ch. Lastly, inefficient string operations can reduce performance, especially for large inputs. Repeated slicing and concatenation should be minimized by combining operations wherever possible to improve efficiency. Edge cases are another critical area that developers often overlook. For example, failing to handle scenarios like an empty string, or ch being the first or last character, can cause unexpected errors. Testing your solution against these edge cases is essential to ensure reliability. From an interview perspective, it's helpful to break the problem into two straightforward steps: locating the index of ch and reversing the prefix. Keeping these steps clear will help you avoid common pitfalls. Recognizing the underlying pattern is also valuable. This problem is essentially a variation of substring manipulation, which is a frequent topic in coding interviews. Efficiently finding characters and manipulating substrings is a skill worth mastering. Moreover, if the interviewer asks about optimization, emphasize how your solution minimizes operations, achieving a linear time complexity of O(n). Lastly, clearly communicating how your solution handles edge cases can leave a strong impression. It demonstrates both thoroughness and attention to detail. This problem is closely related to several others on LeetCode that build foundational string manipulation skills. For instance, in LeetCode 344, you'll focus on reversing an entire string, which is a simpler concept but directly ties into this problem. In LeetCode 541, you'll practice reversing specific parts of a string, which introduces selective reversal, a technique that overlaps with this task. Similarly, LeetCode 557 asks you to reverse individual words in a sentence, and LeetCode 151 takes it a step further by requiring you to reverse the order of words in a string. These problems collectively reinforce the concepts you'll need for efficient string manipulation. As for alternative approaches, one option is the two-pointer technique. Instead of slicing, you can reverse the prefix directly by swapping characters from both ends of the substring, which avoids creating additional substrings and saves space. However, this method can be slightly more complex to implement. Another approach is manually manipulating the string as a character array. Convert the string to a list, reverse the prefix, and then rejoin it. This is particularly useful in languages where strings are immutable, but it introduces a slight overhead due to the conversion process. An even more streamlined approach is to create a one-pass solution that avoids explicit reversal altogether. Instead of first reversing the prefix and then concatenating it with the suffix, you could directly build the result by traversing the string once and appending the reversed prefix and remaining suffix dynamically. While this method can optimize for operations, it's less intuitive and might be harder to debug, especially under time constraints. The trade-off here is between simplicity and operational efficiency, so consider the context in which you're solving the problem, whether it's for an interview or a production scenario, when choosing your approach. Great job! To summarize, we solved the reverse prefix of word problem using efficient string manipulation techniques. Remember to practice more string-related problems to sharpen your skills. Thanks for tuning in, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!